Imagine a square grid populated entirely by positive and negative ones. In discrete mathematics, we use these values to build a balanced structure. The governing rule is that any two distinct rows must be balanced against each other. For this balance, exactly half their entries must match, and the other half must be opposites. Multiplying them element by element, they cancel each other out. The resulting sum is exactly 0, a calculation mathematicians call the dot product. When the dot product of two vectors is 0, they are considered orthogonal. A Hadamard matrix is a theoretical grid where this zero-sum equilibrium of orthogonality exists between every possible pair of rows in the matrix. In 1893, Jacques Hadamard demonstrated that these matrices can only exist at sizes of 1, 2, or multiples of 4. This established the Hadamard Conjecture, the claim that for every multiple of 4 out to infinity, a perfectly orthogonal matrix can be constructed. For 130 years, researchers have successfully built these matrices for every valid size up to 664. At size 668, the sequence stops. A 668 by 668 grid is the smallest unsolved order remaining in this branch of mathematics. Computing power is not the bottleneck preventing this construction. Instead, the number 668 possesses a specific combination of mathematical properties that resists every known shortcut. To find the source of this resistance, we check the pre-sheaf ledger, a master catalog of 19 distinct methods used to build Hadamard matrices. The Sylvester construction is the oldest tool in the ledger. It builds larger matrices by doubling smaller ones. This method is inapplicable here because it requires the target size to be a power of 2. 668 does not fit this requirement. We move to the Paley constructions, which require n-1 or half n-1 to be a prime power. Type 1, 668 minus 1 is 667, or 23 times 29, blocked. Type 2, half of 668 minus 1 is 333, or 9 times 37, also blocked. The arithmetic properties of 668 and its neighbors mean the two most efficient tools in number theory cannot be used. Researchers next attempt the co-cyclic construction. This method uses the symmetries of algebraic groups to generate the matrix entries. This requires mapping abstract group structures that match the order of 668. There are exactly 4 groups of order 668, including cyclic and dihedral structures. Between them, there are 20 possible functions, or cocycle classes, that could generate the matrix. Exhaustive computer checks tested all 20 classes. Every single one produced a non-Hadamard matrix. This confirms that no matrix of order 668 can be built using algebraic group symmetries. That entire branch of research is now closed. Mathematicians then turn to combinatorics and the Williamson construction. This method attempts to build the matrix by assembling 4 symmetric 167 by 167 blocks. Searching for these blocks without a shortcut requires evaluating 2 to the 84th power possible combinations. To manage this scale, we use automorphisms, internal rotational symmetries, to group similar sequences together and reduce the search space. For order 167, these symmetries are usually represented as 83 distinct pairs of entries. However, at 167, the rotation rules trigger an orbit collapse. All 83 distinct pairs merge into a single orbit. This collapse reduces billions of potential candidates into just 256 simple, trivial sequences. Every single one of those 256 candidates has been rigorously tested, and none of them satisfy the Hadamard condition. Further analysis, known as J-cancellation, proves the algebraic structure forces certain values to cancel out, making a valid construction impossible within this subspace. The symmetries that typically aid mathematicians actually trigger a structural collapse at order 668, neutralizing the Williamson construction. Because no structural shortcuts work, researchers are forced into raw computational optimization. The most versatile remaining tool is the Goethals-Seidel method. It treats the matrix blocks as frequencies in a power spectrum. This chart represents the spectral power at different frequencies. For the construction to succeed, the 4 matrix blocks must sum together to create a perfectly flat line at exactly 668. To reach this target, we use simulated annealing, a computational method that makes random changes to the entries, attempting to lower the total error or spectral defect. Researchers typically seed this algorithm with the Legendre sequence, which is the mathematically closest known pattern to the target. This creates the Legendre trap. The sequence's power spectrum produces 168 at non-zero frequencies. 4 copies result in 672, an excess of 4 per frequency, and a severe deficit at 0. This results in a local minimum. The error is so concentrated that the algorithm cannot find any single bit change that would reduce the defect. The search remains stuck. Heuristic algorithms cannot navigate this landscape because the mathematical structure itself contains these inescapable local minima. Without any theory to guide the search, the remaining space is 2 to the 668th power. The final classical attempt uses Turin-type sequences to bridge the gap. Constructing H668 via this method requires finding a sequence called TT56. As of 2025, the furthest known sequence is TT44. TT56 is 12 steps away. Historically, each step in the sequence requires years of dedicated cluster computing time. Quantum approximate optimization algorithms, or QAOA, could theoretically search this space. However, solving for order 668 requires tens of thousands of stable logical qubits, which exceeds the capacity of current quantum hardware. New attempts involve modular Galilei quadruples, or the Propus array, but these remain experimental. There is no mathematical proof that H668 is impossible. It simply remains out of reach. Order 668 remains the most resistant order in discrete mathematics, proof against prime theory, collapsed by symmetry, and trapped